Imagine a moment where time itself unravels, where the past, present, and future blur into a single, infinite tapestry. What if the ticking clock you rely on is just a shadow of something far more complex and mysterious? Time as we know it might be an illusion, a construct hiding dimensions we've yet to fully comprehend. Today, we're diving into the profound enigma of time, exploring 30 mind-bending theories that challenge everything we think we know about its hidden dimensions. From the block universe where all moments exist simultaneously, to the possibility of time crystals and the end of time itself, this journey will reshape how you perceive the fabric of reality. Understanding these theories isn't just about satisfying curiosity, it's about unlocking a deeper connection to the universe and our place within it. So, stay with me as we unravel the secrets of time and space, one astonishing idea at a time. By the end of this video, you'll see the universe and your own existence in a completely new light. Let's begin. Now turning to the first theory, let's explore the block universe, a mind-bending idea that reshapes how we think about time itself. Picture the universe not as a sequence of events unfolding moment by moment, but as a single, unchanging four-dimensional structure. In this model, the past, present, and future all exist simultaneously like frames in a movie reel. Your childhood, your current moment, and even your distant future are all fixed in place, part of a timeless, eternal block. This concept, often linked to Einstein's theory of relativity, suggests that time's flow is an illusion. What we perceive as moving through time might just be our consciousness navigating this static structure. If true, it raises profound questions about free will, destiny, and the nature of reality. Could it be that every moment is already written and we're simply experiencing it in a linear way? The block universe invites us to rethink our most fundamental assumptions about time and perhaps discover a deeper truth hidden within its timeless layers. Now shifting our focus to the second theory, let's delve into Eternalism, a philosophical perspective that complements the block universe concept but takes it even further. Eternalism suggests that all moments in time, past, present, and future, are equally real and exist simultaneously. Unlike the traditional view of time as a flowing river where the past is gone and the future is yet to come, Eternalism flips this idea on its head. It proposes that time doesn't move at all. Instead, every event from the Big Bang to the distant future is just as real as the moment you're experiencing right now. This challenges our everyday perception of time as something that flows or progresses. If Eternalism is true, then the idea of now is merely a matter of perspective, a point of reference within an eternal, unchanging tapestry of existence. This theory also raises intriguing questions about how we understand cause and effect, memory, and even identity. If the past and future are just as real as the present, does that mean our lives are fixed, or is there still room for change? Eternalism invites us to reconsider not just how we experience time, but how we define reality itself. Now turning to our third theory, let's explore the arrow of time, a concept deeply rooted in the second law of thermodynamics. This law states that in any isolated system, disorder or entropy always increases over time. Think of it like this. If you drop a glass and it shatters, it's easy to see how the pieces scatter into chaos, but it's nearly impossible for those pieces to spontaneously reassemble into a whole glass. This natural movement from order to disorder is what gives time its direction, a one-way street from the past to the future. But why does time seem to move in this direction? The answer lies in the initial conditions of the universe. At the Big Bang, the universe was in an incredibly low entropy state, meaning it was highly ordered. As time has progressed, entropy has steadily increased, creating the arrow we experience. This explains why we remember the past but not the future, and why certain processes like mixing cream into coffee are irreversible. The arrow of time not only helps us understand why time flows in one direction, but also raises profound questions about the ultimate fate of the universe. As entropy continues to increase, what does that mean for the cosmos? Could there ever be a reversal? These are the mysteries that keep scientists and philosophers alike pondering the nature of time itself. Building on our exploration of time's mysteries, let's now shift our focus to Einstein's theory of relativity and its fascinating implications for time dilation. According to Einstein, time is not a fixed, universal constant, but rather a flexible dimension that can be stretched or compressed depending on gravity and velocity. Imagine two identical clocks, one placed on Earth and the other sent into space aboard a fast-moving satellite. Due to the satellite's high speed and weaker gravitational field compared to Earth, time on the satellite actually ticks slightly faster. This isn't just a theoretical idea, it's a practical reality for GPS satellites, which must account for these tiny time differences to provide accurate location data. If they didn't adjust for time dilation, GPS systems would be off by several kilometers within minutes. Another striking example comes from astronauts. When they spend extended periods in orbit where gravity is weaker and speeds are higher, they age a fraction of a second less than people on Earth. This phenomenon, though small, has been confirmed through precise experiments. So, what does this mean for our understanding of time? It reveals that time is deeply intertwined with the fabric of the universe, shaped by the forces of gravity and motion. It challenges our everyday experience of time as something uniform and absolute, showing instead that it's a dynamic and relative dimension. As we continue to explore these ideas, we're reminded of just how much there is to uncover about the true nature of time. Now turning to another mind-bending theory, let's explore the many worlds interpretation of quantum mechanics and its implications for time. According to this idea, every decision or event doesn't just follow a single path, it branches off into multiple parallel timelines. Picture standing at a crossroads, choosing to go left or right. In this theory, both choices happen but in different universes. One version of you goes left while another version goes right, and both realities coexist simultaneously. This means that for every moment of your life, countless alternate versions of you are living out every possible outcome in parallel worlds. It's not just about big decisions either. Even the tiniest quantum events, like the spin of a particle, can create new branches. The many worlds interpretation challenges our linear view of time, suggesting that all possible timelines exist at once, each equally real. So, what does this mean for the concept of time? Instead of a single, straightforward flow, time becomes a vast, branching tree of possibilities. This theory raises fascinating questions about free will, destiny, and the nature of reality itself. If every choice leads to a new universe, then every moment is a gateway to infinite possibilities. As we continue to unpack these theories, we're reminded of just how strange and expansive the cosmos truly is. Shifting our perspective to another fascinating concept, let's explore closed time-like curves and their implications for time. In this theory, time isn't just a straight line flowing from past to future. It can loop back on itself, creating a path where the end connects to the beginning. Imagine drawing a line that eventually curves around to meet its starting point, forming a circle. That's essentially what a closed time-like curve is, a loop in space-time where an object or person could, in theory, return to their own past. This idea isn't just science fiction. It's rooted in the equations of general relativity, which suggest that under certain extreme conditions, like near a rotating black hole, such loops could exist. But what would this mean for time travel? If closed time-like curves are possible, they open up the possibility of traveling back in time and potentially altering past events. However, this raises some mind-bending questions about causality and paradoxes, like the classic grandfather paradox, where changing the past could erase your own existence. While the existence of closed timelike curves remains theoretical, they challenge our understanding of time as a linear, one-way journey. Instead, time could be more like a tangled web, full of loops and intersections, where the past, present, and future might coexist in ways we're only beginning to imagine. As we continue to unravel these mysteries, we're reminded that the universe's secrets are far stranger than we often realize. Now turning to a cosmic rhythm that defies our everyday perception of time, we delve into the Big Bounce theory. This idea suggests that the universe isn't a one-time event, but instead goes through endless cycles of expansion and contraction. Picture this: the universe expands outward, like a giant balloon inflating, until it reaches a point where it begins to collapse back in on itself. Then, instead of ending in a singularity, it bounces back, starting the process all over again. This cyclical nature of the universe implies that time itself could reset with each bounce, creating an infinite loop of beginnings and endings. What's fascinating is that this theory offers an alternative to the Big Bang, suggesting that our universe might not have started from nothing but instead emerged from a previous contracting phase. If the Big Bounce is true, it means that time isn't linear in the grand scheme of things, but rather part of a repeating pattern. Each cycle could bring with it new laws of physics, new configurations of space, and entirely different timelines. While this remains a theoretical concept, it challenges us to think beyond our current universe and consider the possibility of an eternal cosmic dance, where time is not a one-way street but a recurring melody in the symphony of existence. Now shifting our gaze to a concept that reimagines the very fabric of reality, let us explore the holographic principle. This groundbreaking idea suggests that everything we perceive in our three-dimensional universe, including time and space, might actually emerge from a two-dimensional surface. Think of it like a hologram. The image you see appears to have depth and dimension, but it's all encoded on a flat surface. In the same way, the holographic principle proposes that the complexity of space-time, with its curves, gravity, and even the flow of time, could be projected from a simpler, two-dimensional boundary. This principle challenges our traditional understanding of how the universe works, suggesting that the richness of our three-dimensional experience might be an illusion, a kind of cosmic projection. What's even more astonishing is that this idea could bridge the gap between quantum mechanics and general relativity, two pillars of physics that have long seemed incompatible. If the holographic principle holds true, it means that everything we experience, past, present, and future, is encoded on this two-dimensional surface. Time itself becomes a phenomenon that emerges from this deeper, more fundamental layer. While this remains a speculative theory, it invites us to rethink the nature of reality, suggesting that the universe might be far more interconnected and mysterious than we ever imagined. As we peel back the layers of this concept, we're left wondering, what if time and space are not fundamental but instead a grand illusion, a projection of something far simpler yet profoundly profound? Now shifting our attention to a fascinating breakthrough in physics, we delve into the concept of time crystals. Unlike traditional matter, which repeats its structure in space, time crystals are a unique phase of matter that repeats its pattern in time. Imagine a clock that ticks not because of an external force, but because its own structure naturally oscillates over time. This remarkable discovery challenges our conventional understanding of equilibrium, which typically refers to a state of rest or balance. Time crystals, however, exist in a perpetual state of motion, breaking the symmetry of time itself. They were first theorized in 2012 by Nobel laureate Frank Wilczek, and their existence was experimentally confirmed in 2017. This new phase of matter opens up intriguing possibilities, suggesting that time, much like space, can host ordered structures. What makes time crystals even more remarkable is their potential to operate at the lowest possible energy states, meaning they can sustain their oscillations without requiring an external energy source. This property could have profound implications for fields like quantum computing, where stable, low-energy systems are crucial. As we explore this groundbreaking concept, we're left to wonder, could time crystals be the key to unlocking new dimensions of time, or even reshaping our understanding of the universe's fundamental laws? The journey into this uncharted territory continues to reveal just how much we still have to learn about the nature of reality. Shifting our gaze to the distant future, we confront a theory as unsettling as it is profound, the end of time itself. In scenarios like the heat death of the universe, scientists propose that time could effectively cease to exist. This concept stems from the second law of thermodynamics, which tells us that the universe is gradually moving toward a state of maximum entropy, where all energy is evenly distributed and no work can be done. In this state, known as the heat death, the universe would reach a point of complete thermal equilibrium. Without any energy gradients or changes, time as we understand it would lose its meaning. There would be no events, no processes, and no way to measure the passage of time. This idea challenges our fundamental perception of time as a constant, ever-flowing entity. It suggests that time is not an absolute but a feature dependent on the universe's dynamic processes. What's even more thought-provoking is the possibility that this theoretical end of time might not just apply to the far future. Some models predict that, in certain regions of the universe, time could already be slowing down or ceasing altogether. As we ponder these ideas, we're left to wonder, could the end of time be the ultimate destiny of the cosmos? This theory invites us to reconsider not just the nature of time, but the very fabric of existence itself. Now shifting our perspective, we delve into a theory that challenges the very foundation of our understanding, the idea that time is nothing more than an illusion. This concept suggests that time is not an inherent feature of the universe but rather a construct of human consciousness. In other words, what we perceive as the passage of time might simply be a mental framework that helps us make sense of the world around us. Physicists and philosophers alike have long debated this idea, pointing to the way our brains process information in sequences. For instance, we experience events as happening in a linear order, but this could be a result of how our minds organize memories and sensations, not an objective reality. Many argue that the physical universe exists in a timeless state where all moments past, present, and future are equally real. This aligns with the block universe theory we discussed earlier, where time is seen as a dimension rather than a flowing river. What's fascinating is how this theory intersects with our understanding of consciousness. If time is indeed a mental construct, then our perception of its passage could vary depending on our state of mind. Think about how time seems to fly when we're engrossed in an activity or drags when we're bored. These subjective experiences hint at the possibility that time is shaped by our awareness rather than an external force. This theory invites us to question whether time exists independently or if it's a tool our minds use to navigate reality. By exploring this idea, we're not just redefining time, we're redefining our place within the universe. Now stepping into the realm of quantum theory, we encounter the Wheeler-DeWitt equation, a groundbreaking attempt to reconcile two of the most profound theories in physics, quantum mechanics and general relativity. Proposed in the 1960s by physicists John Wheeler and Bryce DeWitt, this equation seeks to describe the universe in its entirety without relying on the concept of time. Instead, it treats the universe as a timeless, static entity, a stark departure from our everyday experience of time's flow. At its core, the Wheeler-DeWitt equation suggests that time, as we know it, might not be a fundamental feature of the cosmos, but rather an emergent property that arises from deeper, more fundamental interactions. This idea aligns with the notion of a frozen universe, where all possible configurations of space and matter exist simultaneously, and the passage of time is an illusion. The implications of this theory are profound. If the equation holds true, it would mean that our perception of time is akin to watching a single frame of a movie, while the entire film already exists in its entirety. Critics argue that this perspective conflicts with our intuitive understanding of causality and change, but proponents see it as a way to bridge the gap between the quantum and cosmic scales. By eliminating time from the equation, the Wheeler-DeWitt theory challenges us to rethink the very fabric of reality, pushing the boundaries of what we consider possible in our understanding of the universe. Now exploring the vast possibilities of the multiverse, we venture into a theory that stretches the boundaries of imagination, the idea of infinite universes coexisting, each with its own unique timeline and set of physical laws. This concept, rooted in the multiverse theory, suggests that our universe is just one among countless others, each operating independently yet simultaneously. Picture a vast cosmic tapestry where every thread represents a different universe, each weaving its own story of time and existence. In some of these universes, time might flow backward, while in others it could loop endlessly or even stand still. The laws of physics we take for granted, gravity, electromagnetism, and even the speed of light, could vary dramatically from one universe to the next. This theory challenges the notion that time is a universal constant, proposing instead that it is a flexible, localized phenomenon shaped by the unique conditions of each universe. The multiverse idea emerges from various branches of physics, including quantum mechanics and string theory, where the potential for multiple realities arises naturally from mathematical equations. While the concept may seem like science fiction, it offers a compelling explanation for the fine-tuning of our universe. Why does our universe have the precise conditions needed for life? In a multiverse, it's simply one possibility among an infinite array of outcomes. Critics question how we could ever test or observe these other universes, but proponents argue that the multiverse theory provides a framework for understanding the deeper mysteries of existence. By embracing the idea of infinite timelines, we open the door to a richer, more expansive understanding of time itself, where the constraints of a single universe no longer limit our imagination. Now shifting our focus to a fundamental force shaping the universe, we delve into the intricate relationship between entropy and time. Entropy, often described as the measure of disorder in a system, plays a crucial role in defining the arrow of time. According to the second law of thermodynamics, entropy in a closed system always increases over time, moving from order to chaos. This irreversible process gives time its direction, distinguishing the past from the future. Imagine a sandcastle slowly eroding under the force of wind and waves. The once orderly structure gradually becomes a scattered pile of sand, a perfect illustration of entropy at work. In the universe, this same principle applies on a cosmic scale. Stars burn out, galaxies disperse, and even the vast cosmic structures we see today will eventually succumb to the relentless march of entropy. Yet, this isn't just a story of decay, it's also the driving force behind complexity and life itself. The increase in entropy allows for energy to flow and systems to evolve, creating the conditions necessary for planets, ecosystems, and conscious beings to emerge. Without entropy, time would lose its meaning and the universe would remain stagnant. This raises profound questions. Could a universe without entropy exist? And if so, would time itself cease to flow? By understanding entropy's role, we gain insight into why time moves forward and how it shapes the evolution of everything around us. From the smallest particles to the largest galaxies, entropy is the unseen hand guiding the universe's journey through time. Now venturing into one of the most mind-bending concepts in time theory, we encounter the bootstrap paradox. Imagine a scenario where an object, piece of information, or even an event exists without a clear origin, essentially creating itself in a closed loop of time. This paradox gets its name from the idea of pulling oneself up by the bootstraps. an impossible feat that mirrors the impossibility of explaining how such a loop begins. Let's take a classic example. Imagine a time traveler goes back in time and gives a famous musician a song they didn't yet write. The musician then records the song and it becomes a hit. But who really wrote the song? The time traveler received it from the future, and the musician only knows it because the traveler brought it back. In this loop, the song has no true creator, it just exists. This raises profound questions about causality and the nature of reality. If events can be self-causing, does that mean the past, present, and future are intertwined in ways we can't fully grasp? Could the universe operate in cycles where certain events are destined to repeat with no beginning or end? While the bootstrap paradox challenges our understanding of cause and effect, it also opens the door to intriguing possibilities about the structure of time. Could such loops explain phenomena we observe today, or are they merely theoretical puzzles? As we explore this paradox, we're reminded that time, in all its complexity, continues to defy our attempts to fully understand it. Now shifting our focus to another fascinating puzzle in the realm of time travel, we arrive at the grandfather paradox. This thought experiment poses a perplexing question. What would happen if you traveled back in time and prevented your own grandfather from meeting your grandmother? Without their union, your parent, and by extension, you would never exist. But if you were never born, how could you have traveled back in time to alter the past in the first place? This paradox challenges the very consistency of timelines and causality, suggesting that certain actions in the past could create impossible contradictions. It forces us to consider whether the universe has built-in mechanisms to prevent such paradoxes, or if they remain purely theoretical. Some scientists propose that the grandfather paradox could be resolved through the idea of parallel universes, where altering the past simply creates a new timeline rather than erasing the original one. Others argue that the paradox highlights the impossibility of backward time travel altogether, as it would disrupt the fundamental laws of cause and effect. Regardless of the interpretation, the grandfather paradox serves as a powerful reminder of the intricate and often baffling nature of time. It pushes us to question not just how time works, but whether it's possible to change the past and what consequences such changes might have on the fabric of reality. Now turning to a fascinating resolution to the grandfather paradox, we encounter the Novakov self-consistency principle. This idea, proposed by physicist Igor Novakov, offers a compelling solution to the problem of time travel paradoxes. Essentially, the principle states that any action taken by a time traveler in the past must be consistent with the events that have already occurred. In other words, if you traveled back in time, you couldn't create a paradox because the universe would naturally adjust to ensure that your actions align with the established timeline. For example, even if you attempted to prevent your grandparents from meeting, something would inevitably intervene to preserve their union, ensuring your own existence and the consistency of history. This principle suggests that the universe has a sort of built-in safeguard against paradoxes, making it impossible to alter the past in a way that creates contradictions. It's a reassuring idea in some ways, as it implies that the fabric of reality is robust and self-correcting. However, it also raises questions about free will and determinism. If every action in the past is predetermined to maintain consistency, does that mean our choices are an illusion? The Novakov self-consistency principle doesn't provide all the answers, but it offers a thought-provoking perspective on the nature of time and causality. It challenges us to rethink what's possible in the realm of time travel and consider how the universe might enforce its own rules to preserve order. Now shifting our focus to the intriguing world of loop quantum gravity, we explore a theory that redefines time as a granular, quantized entity. Unlike the smooth, continuous flow of time we experience in our everyday lives, loop quantum gravity suggests that time is composed of tiny, indivisible units, much like pixels on a screen or grains of sand on a beach. This theory emerges from the attempt to reconcile Einstein's general relativity with quantum mechanics, aiming to describe the fabric of spacetime at the smallest possible scales. In this framework, spacetime isn't a smooth continuum but a network of interconnected loops akin to a finely woven tapestry. Time, within this model, becomes discrete, meaning it occurs in distinct, quantized steps rather than flowing seamlessly. This radical idea challenges our conventional understanding of time's nature, proposing that even time itself is subject to the rules of quantum mechanics. One of the most fascinating implications of this theory is the potential resolution it offers to the problem of singularities, such as those found at the center of black holes. Instead of infinite density, loop quantum gravity suggests that spacetime reaches a smallest possible scale, preventing the breakdown of physical laws. While this theory is still in its developmental stages and remains unproven, it opens up profound questions about the fundamental structure of reality. If time is granular, what does that mean for our perception of its flow? Could there be a smallest unit of time that we've yet to detect? Loop quantum gravity invites us to rethink not just time, but the very nature of the universe itself. As we continue our journey through these theories, this perspective reminds us that the mysteries of time are still far from fully unraveled. Now, setting our sights on the simulation hypothesis, we dive into a theory that proposes a radical reimagining of time itself. What if our entire reality, including time, is nothing more than an advanced simulation? This idea suggests that time is not a fundamental aspect of the universe but a programmed construct, much like the ticking clock in a video game. In this framework, the flow of time could be a carefully coded feature designed to create the illusion of progression and continuity. Proponents of this hypothesis argue that if we live in a simulation, time might be quantized and controlled by the underlying code, operating in discrete steps rather than a smooth, continuous stream. This raises intriguing questions about free will, causality, and the nature of existence. If time is programmable, could it be paused, rewound, or even altered by the creators of the simulation? The simulation hypothesis also challenges our understanding of reality itself, blurring the line between the physical and the digital. While this theory remains speculative and lacks empirical evidence, it invites us to consider the possibility that our perception of time is not as concrete as it seems. As we explore this mind-bending idea, it reminds us that the mysteries of time are not just about its nature, but also about the very foundation of our reality. Moving forward, this perspective opens the door to even more profound questions about the universe and our place within it. Now, shifting our focus to string theory, we enter a realm where time takes on a truly multidimensional character. String theory proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings exist in higher dimensions beyond the familiar 3 of space and 1 of time we experience. In this framework, time emerges from the complex interactions of these strings, weaving together the fabric of space-time in ways that challenge our everyday understanding. Imagine time not as a straight line, but as a dynamic, multidimensional tapestry shaped by the vibrations of these fundamental strings. This perspective suggests that time could vary in ways we can't yet perceive, influenced by the geometry of these hidden dimensions. String theory also introduces the idea of brain's membranes existing in higher dimensions that could play a role in how time unfolds across different regions of the universe. While these concepts are highly theoretical and difficult to test experimentally, they offer a fascinating glimpse into how time might operate on the most fundamental level. By exploring string theory's interpretation of time, we're reminded that our perceptions may only scratch the surface of a far more intricate and interconnected reality. Now, turning to the origins of time, we delve into one of the most profound questions in cosmology. What existed before the Big Bang, and did time itself have a beginning? The Big Bang theory describes the expansion of the universe from an incredibly hot and dense state, but it doesn't explain what, if anything, came before it. Some theories suggest that time itself began at the moment of the Big Bang, meaning there was no before in the traditional sense. In this view, time is a fundamental property that emerged alongside space and matter, creating the framework for the universe as we know it. However, other theories propose that the Big Bang wasn't the absolute beginning but rather a transition from a previous state. For instance, the idea of a big bounce suggests that our universe could be part of an endless cycle of expansion and contraction, with time stretching infinitely in both directions. Another intriguing concept is the multiverse theory, where our universe is just one of many, each with its own timeline and physical laws. In this scenario, time might have existed in other universes long before ours came into being. Quantum gravity theories also offer alternative perspectives, suggesting that time could emerge from more fundamental, timeless processes at the quantum level. While these ideas are still speculative, they challenge us to rethink the very nature of time and its origins. Was there truly a beginning, or is time an eternal, unending dimension? As we explore these possibilities, we're reminded that the mysteries of time continue to stretch far beyond our current understanding, inviting us to question the very foundations of reality. As we venture deeper into the mysteries of time, we now turn our attention to the intriguing connection between consciousness and the perception of time. Theories in this realm suggest that our awareness of time's passage might not be an objective feature of the universe, but rather a construct of our own minds. In other words, the flow of time could be an illusion created by the way our brains process information. One compelling idea is that consciousness operates in discrete moments, stitching them together to create the sensation of a continuous timeline. This means what we experience as the present is actually a series of snapshots, with our minds filling in the gaps to create a seamless narrative. Another perspective comes from quantum mechanics, where some interpretations propose that observation itself by a conscious observer plays a role in shaping reality, including the flow of time. This raises fascinating questions. Could time exist without consciousness, or is it our awareness that gives time its meaning? These theories challenge the traditional view of time as an independent, unchanging dimension, suggesting instead that it's deeply intertwined with the way we experience the world. While these ideas are still debated, they invite us to consider how much of what we perceive as reality is shaped by our own minds. As we ponder the role of consciousness in time, we're reminded that the mysteries of the universe may be as much about us as they are about the cosmos. Now exploring the enigmatic realm of black holes, we find ourselves at the edge of one of the universe's most fascinating phenomena. Black holes, with their immense gravitational pull, distort not just space but time itself. Imagine standing near the event horizon, the point of no return. From your perspective, time would appear to flow normally, but to an outside observer, your clock would seem to slow down dramatically. This is known as time dilation, a concept rooted in Einstein's theory of general relativity. The closer you get to a black hole, the more extreme this effect becomes, stretching seconds into what might seem like hours or even years for those watching from afar. This is because the immense gravity of a black hole warps spacetime, bending it in ways that alter the very fabric of time. Another mind-bending aspect is spacetime curvature. In the vicinity of a black hole, spacetime is so distorted that it resembles a funnel, with the black hole at its center. This curvature not only affects the passage of time, but also the paths of light and matter, pulling them inexorably toward the singularity at the core. Some theories even suggest that at the heart of a black hole, time might cease to exist entirely, or it could loop back on itself in strange and unpredictable ways. While black holes remain shrouded in mystery, they offer a unique window into the relationship between gravity, spacetime, and time itself. As we contemplate these cosmic giants, we're reminded of just how much the universe still has to teach us about the nature of time. Now shifting our focus to the quantum realm, we encounter one of the most puzzling phenomena in physics, quantum entanglement. This intriguing concept suggests that particles can become linked in such a way that the state of one instantly influences the state of another, no matter the distance separating them. But what if this connection isn't just limited to space? What if it stretches across time as well? In the world of quantum mechanics, entangled particles seem to communicate instantaneously, defying the classical notion that nothing can travel faster than the speed of light. This has led scientists to explore the possibility that entanglement might transcend time itself, creating connections that bridge past, present, and future. Imagine two entangled particles separated by time rather than space. If one particle is measured in the present, its entangled counterpart in the past or future could instantly adopt a corresponding state, effectively communicating across time. This idea challenges our traditional understanding of causality, the principle that cause must always precede effect. In the quantum realm, cause and effect might not follow a straightforward timeline, opening the door to possibilities where events could influence each other in ways that seem to defy logic. Some experiments have even hinted at this, suggesting that measurements performed on entangled particles could influence their counterparts in ways that appear to flow backward through time. While the full implications of this are still being explored, quantum entanglement offers a tantalizing glimpse into how time might function on the smallest scales. It's a reminder that in the quantum world, the rules we take for granted in our everyday lives may not always apply, and that time itself could be far more fluid and interconnected than we've ever imagined. Now shifting our gaze to the grand cosmic scale, we encounter the theory of eternal inflation, a concept that redefines our understanding of the universe's infinite nature. Imagine a cosmos that doesn't just expand, but does so endlessly, like a balloon that never stops growing. Eternal inflation suggests that our universe is just one of countless bubbles in an ever-expanding multiverse, each bubble harboring its own unique timeline and set of physical laws. In this scenario, the Big Bang wasn't a singular event, but rather a localized occurrence within an infinite sea of inflating space. As these bubbles expand, they give birth to new universes, each branching off into its own distinct reality. This means that time itself isn't linear or finite, but instead part of an infinite tapestry where every possible outcome unfolds somewhere in the multiverse. The implications are staggering. If eternal inflation is true, then there could be an infinite number of versions of you, me, and everything we know, each existing in a parallel universe with its own timeline. While this idea challenges our intuitive grasp of reality, it offers a breathtaking perspective on the universe's vastness and the infinite possibilities it holds. Eternal inflation invites us to consider that time, space, and existence might be far more complex and interconnected than we've ever imagined, opening the door to a cosmos that is endlessly diverse and endlessly expanding. Now turning to the mysterious force shaping the very fabric of our universe, we delve into the role of dark energy in time. Dark energy, that enigmatic force driving the accelerated expansion of the universe, doesn't just stretch space, it also influences how we perceive and experience time. As the universe expands faster and faster, galaxies move farther apart and the distances between them grow exponentially. This acceleration has profound implications for time itself. In a universe dominated by dark energy, the future could see galaxies so far apart that they become invisible to one another, effectively isolating regions of space and time. This cosmic expansion could mean that time, as we know it, becomes fragmented or even ceases to have meaning in distant regions of the universe. Moreover, dark energy's influence challenges our understanding of time's arrow, the idea that time moves in one direction from past to future. If the universe's expansion continues unchecked, it could lead to a future where time's flow becomes less predictable or uniform. Some theories even suggest that dark energy could alter the fundamental nature of time, stretching it in ways we can't yet fully comprehend. By exploring dark energy's role, we begin to see how deeply intertwined time is with the universe's expansion, offering a new perspective on the forces that shape our reality. This theory not only deepens our understanding of time, but also highlights the profound mysteries that still await us in the cosmos. Building on the mysteries of dark energy, we now shift our focus to a groundbreaking concept that redefines our understanding of time and space, the holographic universe. Imagine the universe as a vast, intricate hologram, where the three-dimensional reality we experience is actually a projection from a two-dimensional surface. This idea, known as the holographic principle, suggests that time, like space, may not be as fundamental as we once thought. Instead, time could emerge from the interactions of information encoded on this two-dimensional boundary. It's like watching a movie projected from a flat screen. What we perceive as the passage of time might simply be the unfolding of data from a higher dimensional source. This theory challenges the very notion of time as an independent entity, proposing that it's deeply connected to the way information is processed and manifested in the universe. If the holographic principle holds true, it could mean that time is not a linear, continuous flow, but a complex, emergent phenomenon shaped by the deeper structure of reality. By exploring this idea, we open up new possibilities for understanding the nature of time and its relationship to the fabric of the cosmos. This perspective not only shifts how we view the universe, but also invites us to consider the profound interplay between information, dimensions, and the very essence of existence. Now, stepping into the realm of quantum mechanics, we encounter a phenomenon that seems to bend our understanding of time itself, the quantum Xeno effect. This intriguing concept suggests that time can be slowed down or even appear frozen simply through the act of observation. Here's how it works. In quantum systems, particles exist in multiple states simultaneously, a phenomenon known as superposition. However, when we observe or measure the system, the particle collapses into a single state. The quantum Xeno effect proposes that if we repeatedly observe the system in quick succession, we can essentially freeze it in its initial state, preventing it from evolving as it normally would. It's like repeatedly checking on a pot of water to see if it's boiling. If you check too often, the water never has the chance to heat up. This effect challenges our traditional view of time as a constant, unyielding force. Instead, it suggests that time's flow might be influenced by how we interact with the universe at the quantum level. While this concept is still largely theoretical and primarily observed in controlled experiments, it opens up fascinating possibilities. Could time, at least on a quantum scale, be manipulated through observation? And what implications would this have for our understanding of reality? By exploring the quantum Xeno effect, we delve into the strange and fascinating interplay between time, observation, and the fundamental nature of existence. Now shifting our focus to a groundbreaking perspective, let's explore the theory of emergent time. This idea proposes that time isn't a fundamental feature of the universe, but rather something that arises from more basic processes like quantum interactions or the flow of information. Imagine time not as a river flowing on its own, but as a pattern that emerges from the intricate dance of particles and forces. In this view, time is more like a byproduct, a consequence of how the universe organizes itself at its most fundamental level. For example, in quantum mechanics, particles interact in ways that create sequences of events, and it's these sequences that give us the illusion of time moving forward. Similarly, in information theory, time could be seen as a way to track changes in the state of a system, like a clock ticking as information is processed. This theory challenges the traditional notion of time as an independent dimension, and instead suggests it's woven into the very fabric of reality through deeper mechanisms. By examining emergent time, we confront profound questions about what time truly is and how it might be intricately linked to the fundamental workings of the universe. Could time be more of a construct emerging from the way we perceive and interpret the cosmos? As we unpack this theory, we step closer to understanding whether time is an inherent feature of reality or simply a shadow cast by its underlying processes. Now delving into the final theory of our exploration, we re-examine the profound role of gravity in shaping our understanding of time. Gravity, as described by Einstein's theory of general relativity, doesn't just pull objects toward one another, it also warps the very fabric of space-time itself. This means that time doesn't tick at the same rate everywhere in the universe. Near massive objects like planets or black holes, time slows down compared to areas with weaker gravitational pull. This phenomenon, known as gravitational time dilation, has been confirmed through experiments such as comparing clocks on Earth's surface to those on high-altitude satellites. But gravity's relationship with time goes even deeper in modern physics. In theories of quantum gravity, which aim to unify general relativity with quantum mechanics, gravity is thought to play a fundamental role in the emergence of time itself. Some physicists propose that time may not exist at the smallest scales of the universe, and gravity could be the force that stitches together the fabric of space-time, giving rise to the flow of time we experience. This raises fascinating questions. Could gravity be the key to understanding time's origins? And if so, how does this reshape our view of the universe? As we wrap up this journey through 30 mind-bending theories, we're left with a deeper appreciation for the intricate and mysterious relationship between gravity and time, one that continues to challenge and inspire our understanding of the cosmos. As we bring this journey to a close, it's clear that the 30 theories we've explored today paint a picture of time as far more than a simple ticking clock. From the block universe to time crystals, from the holographic principle to the role of gravity, each theory offers a unique lens through which to view the hidden dimensions of time. Together, they challenge our fundamental assumptions about existence, suggesting that time might be an illusion, a construct, or even an emergent property of deeper forces at work in the universe. These ideas not only expand our understanding of physics, but also invite us to rethink our place in the cosmos. The beauty of these theories lies in their ability to inspire curiosity and wonder. They remind us that the universe is full of mysteries waiting to be unraveled, and that our quest to understand time is far from over. We've only scratched the surface, and every discovery leads to new questions, new possibilities, and new frontiers of exploration. So, what do you think? Which of these theories resonated most with you? Do you see time as a fixed structure, a flowing river, or something entirely different? Share your thoughts in the comments below. We'd love to hear your perspectives and spark a conversation about these mind-bending ideas. If you've enjoyed this deep dive into the hidden dimensions of time, don't forget to hit that like button and subscribe to our channel. There's a universe of mysteries waiting to be explored, and we're just getting started. Until next time, keep questioning, keep wondering, and keep exploring the incredible mysteries of the cosmos.